Hello and welcome back to our next installment in Calculations in Chemistry. This time we're going to be looking at limiting and excess reagents, and this is when we're given more information than we've previously been given. So we're given information on two reagents and we need to know which one's going to be the most important. So let's jump right in. Easiest way to think about this is if we think about an analogy to a sandwich. When we make a sandwich, we want two slices of bread, we want some fillings. When we put the filling and the two slices of bread together, we get a sandwich. And we can call this the chemical equation for a sandwich. So going on with this idea, if we look at the reaction of making sandwiches, we're going to make some pretty simple and basic sandwiches. We're going to take one slice of ham and we're going to have two slices of bread, and this is going to produce a ham sandwich. So we have a ratio of 1 ham, 2 bread to 1 sandwich. If we had 5 pieces of ham and 4 slices of bread, okay, so if we have five pieces of ham and 4 slices of bread, we have an issue in that the ratio now is not 1:2. Okay, so the bread is going to limit how many sandwiches we can make, because I'm going to have 2 sandwiches and I'm going to have used up my 4 slices of bread. So, but in that meantime, I will have only used 2 slices of ham. So I will have 3 slices left over. So this is similar to what we refer to as the limiting factor in a chemical equation. Bread is the limiting factor. Once I've run out of bread, I can't make any more sandwiches. It doesn't matter how much ham I have, there's going to be no more sandwiches because I don't have any more bread. I've run out of one of the required elements of what I'm trying to make. This same situation can happen with chemical reactions. When we perform a reaction, we have a certain amount, we've put into our flask a certain amount in mass, volume, or moles of our reagents, of one or both of the reactants. Many times we've done reactions like when we were looking at the reactions between acids and bases, we put a small piece of magnesium into a large amount of hydrochloric acid. The acid was still present even after all the magnesium had reacted. In this case, our magnesium was the limiting factor. We hadn't used up all the hydrochloric acid, but we had used up all the magnesium. And once all the magnesium reacted, there was no more hydrogen gas being produced. So what we do is we term these as excess and limiting. One of the reactants will limit the amount of product that is formed, i.e. the magnesium ribbon in the hydrochloric acid and magnesium reaction. The other will be in excess. It will be left over after the reaction has finished as far as it can go. So if we look at this, this is the equation for water, and we can think of water being formed from hydrogen gas plus oxygen gas is going to produce H2O. When we balance this equation, we can see that I have 2 oxygens on the left-hand side. So to make 2 oxygens on the right-hand side, I'm going to make 2 waters. This now means I need 4 hydrogens. So I'm going to need 2 hydrogen gas in order to make this. So we can see that this will react in a 2:1:2 ratio. If we look at our first example here, we have 5 molecules of hydrogen and 2 molecules of oxygen. If I was reacting 5 molecules of H2, I can only react 2.5 molecules of O2. So in fact, what we see is that the 2 oxygen molecules that we have, I will require the 4 hydrogen molecules in order to react that. Once that has occurred, the reaction stops. I can't get a half a molecule more of oxygen. So the 2 oxygen molecules react, forming 4 molecules of water, and we leave 1 H2 left over because it was in excess. Okay, so hydrogen here, hydrogen gas is the excess reagent, and oxygen is limiting. Once the oxygen has run out, there's no more water produced. In the example down below, we have 4 molecules of hydrogen and 4 molecules of oxygen. Again, this time we can see that we will have more oxygen than hydrogen because this amount of hydrogen, the 4, is only going to be able to react with 2 molecules of oxygen. Okay, so what I want over what I've got is going to be 2 molecules of oxygen that can react. So we see this again. The 2 molecules of oxygen react to produce 4 molecules of water, using up all the hydrogen gas. And then the O2 gas is in excess in this case. So in this, generally in all reactions, one reactant will be in excess and one will be limiting. So the key vocabulary we need to know for this is that the limiting reagent is the reactant that is completely used up in the chemical reaction. The limiting reagent will determine how much product is produced because it is the one that will run out first. So anytime I want to do calculations to work out the amount of product, I'm going to be using the limiting reagent. The excess reagent is the one that will have some left over after the reaction has finished, has gone as far as it can. It doesn't matter how much more of the limiting reagent, the excess reagent we add in, the reaction won't go any further. I can't make any more product if the limiting reactant has been used up. So if we apply this to chemical equations, it is critical for us to be able to see the mole ratios. We can see that this is a 1:3:2 ratio here in the Haber process, where we react nitrogen with hydrogen gas to form ammonia. Every 1 mole of nitrogen gas will react with 3 moles of hydrogen to produce 2 moles of ammonia. We're told down here if 1 mole of nitrogen and 4 moles of hydrogen are mixed together. So if I have an actual 1 and 4, we're asked how much will be used up and how much will be left over. Well, I have my 1 mole of nitrogen and I require only 3 moles of hydrogen to react with that. So I'm going to have my 4 minus 3, I'm going to have 1 mole left over. And when I have 1 mole left over, okay, I'm still going to get my 2 moles of ammonia, but I will have 1 mole of hydrogen left over. So hydrogen was in excess, my nitrogen was my limiting factor, and then we move on from there. So if we have a look at this question, we can see that a gaseous mixture of hydrogen gas and oxygen gas are mixed and ignited. The waters produced, collected and weighed. What is the expected mass of the water produced? And we're asked what steps to follow to solve the problem. Well, first steps first, we're going to need a balanced equation. Okay, then we're going to need to work out the mole of oxygen present and the mole of hydrogen present. Then we will work out, then we're going to work out which one's going to run out. So let's have a look. So we're going hydrogen plus oxygen is producing water again. We know from before that this is now our balanced equation. We can work out the number of mole of hydrogen. Whoops, getting ahead of myself. Number of mole of hydrogen is going to be equal to 25 divided by 2 because it's H2 gas, which is going to be 12.5 mole. Our number of mole of oxygen is going to be equal to 100 divided by 32. So we're going to have 100 divided by 32 because again we've got O2, which is equal to 3.125 mole. Now what we're going to do is work out how much we would need based on the number of mole of hydrogen. So I'm going to work out if I had that amount of hydrogen, how much oxygen would I need? So what I want over what I've got multiplied by my number of mole of hydrogen. So this means I'm going to need 6.25 mole of oxygen is required to work with that much hydrogen. And if we have a look, I don't have that much. What I have is 3.125 mole. So N of oxygen available, how much was put in the flask, is less than what is required. So this means that oxygen will be my limiting reagent. It will run out before I get the amount of hydrogen reacted that I want. So the amount of water that I can produce will be based on the amount of oxygen because it will run out first. So I can calculate the amount of water based on the number of mole of the limiting reagent, which is my oxygen. So now number of mole of water is going to equal 2 times the number of mole of oxygen from my equation. I know that the number of mole of oxygen I have is 3.125. So it's going to be 2 times 3.125, which is going to be 6.25 mole. That's how much water I will produce. So the mass of water is going to equal 6.25 multiplied by the molar mass, which is 18, which gives us 112.5 grams of oxygen being produced. This may seem a little bit confusing at this point, but let's look at the steps that I followed to get here. First of all, we're going to write down a balanced equation. These are exactly the same as mass-mass stoichiometry. We're going to determine the mole ratio and calculate the number of mole of each reagent, because in limiting and excess, there will always be more than one number of mole that we can determine. That's how we can figure out if it's a limiting and excess versus a standard stoichiometry question. We're going to identify the limiting reagent, so work out which one will run out first. Okay, so we're going to look at one and work out how much we need of the other. Convert the amount of the required substance to units as specified in the question. So do we need it in grams? Do we need it in mole? Calculate the amount of substance required based on the limiting reagent in the equation, i.e. use limiting to work out the product. Okay, I can't use my excess reagent because that will tell me that I'll produce more product than I actually will. Let's look at a couple of examples. Again, this will get quite long because I'm going to go through the worked examples. Feel free to pause the video, have a go at the question yourself, and then just come back for the answer. Okay, so in our first example, we're told that we have an electric furnace that has carbon and silicon dioxide being reacted together, and we're given the equation. So we have 2 carbon reacting with silicon dioxide to produce silicon carbide and carbon dioxide. We're given 40 grams of carbon, so we have a mass and a molar mass, and 40 grams of silicon dioxide. Again, we have a mass and a molar mass because we know the formula here. We're asked to find the limiting reactant, which one is in excess and by what amount, so we need to work out how much will be left over. And the mass of silicon carbide that will be produced. Okay, so we've got a molar mass here, and we will use N of limiting to work this out, to work out N of silicon carbide. So let's start doing that. If you think you can know how to work this out yourself, have a go. Start with working out the mole of each of the reactants that we've been provided information for, and come back and check your answer. Okay, so I'm going to write my equation up here if you want to work along with me. I've got 2 carbon reacting with silicon dioxide is going to produce silicon carbide and CO2. Okay, so from this, we're now going to work out the number of mole of carbon, and we were told we had 40 grams of carbon, so we're going to divide by 12.01 to work out the number of mole of carbon, and this is going to be equal to 3.33 mole. Next, I'm going to work out the number of mole of silicon dioxide because I also have enough information to work that out. So it's going to be 40 divided by silicon and the 2 lots of oxygen, which is going to be a molar mass of 60.1 grams per mole. So when we do this, we get 0.666 0.6 mole of silicon dioxide that is going to react. Okay, so we have the number of mole of carbon, we have the number of mole of silicon dioxide. We can look at the ratio and we can see that the number of mole of silicon dioxide that I require is going to be a half the number of mole of carbon. Okay, so I'm just picking one. So in this case, I'm working out this number of silicon dioxide required to react all the carbon that I have. So if I do that, that's 3.33 multiplied by 0.5. So I'm going to end up with 3.33 multiplied by 0.5, 1.665 mole. That's how much I need. If I have a look here, what I have is 0.66 mole. So N of silicon dioxide available, i.e. what I started with, is less than the N of silicon dioxide required. Okay, so this means that silicon dioxide is limiting. So we've identified the limiting factor, which was the first thing we had to do. So that means carbon is in excess. I need to work out by how much. So N of carbon used is going to equal, well, I want 2/1 of my silicon dioxide, which is my limiting reactant. So I'm going to have 0.666 multiplied by 2 gives me 1.332 mole of carbon will be used. So carbon left over is going to equal 3.33 because that's what I started with, minus the 1.33 that's going to be used. So I'm going to get 2 mole of carbon left. So I've worked out my limiting, I've worked out my excess and how much it is in excess by. The next was to work out the amount of product, okay, of silicon carbide. So I can work out my silicon carbide. I need to use my limiting reactant as the ratio. So I can see that the amount of silicon carbide is equal to 1/1 times the number of mole of silicon dioxide. So they're going to be the same value. We use 0.666 mole of silicon dioxide. So that's how much silicon carbide I will use. So the mass of silicon carbide is going to equal mole multiplied by molar mass. So I'm going to have 0.666 multiplied by the molar mass of silicon carbide, which is going to be 40.1 silicon plus carbon, and I get 26.7 grams of silicon carbide being produced. Hopefully you got that answer as well. I've got another question for us to have a go at. So I recommend this time you pause, have a go yourself, and then come back and see the answer. Okay, so I've worked out my number of mole of aluminium and my number of mole of iodine based on the information that was provided in the question. So now I'm going to look at my equation. I can see that 2 mole of aluminium will react with 3 mole of iodine. So I'm going to work out the number of mole of iodine that will be used for the number of mole of aluminium that I have. So that's going to be a 3/2, what I want, iodine coefficient divided by what I've got, aluminium coefficient, multiplied by the number of mole of iodine, 0.00500, which is going to give me 0.075 mole. So that is the iodine that is required. If I have a look here, I have 0.00998 mole available, which is less than 0.075. So iodine is my limiting reagent. This means that now I will work out the amount of product based on iodine. So in this case, I'm now going to work out the mole of product, aluminium iodide, based on the number of mole of iodine. So my mole ratio will be what I want, which is 2 over what I've got, 3 multiplied by the number of mole of iodine, 8. So this will give me the number of mole of my aluminium iodide that is going to be consumed, okay, which is going to be 2/3 of this is going to be 0.00666 mole. And from here, I can work out the number of mole of the mass of my aluminium iodide. So mass of aluminium iodide is going to equal 0.00666 multiplied by the molar mass, which is quite big because lots of iodine, 0.7. So we will get, even though we have a very small number of mole, 2.71 grams of aluminium iodide being produced. Hopefully you got that answer and you are feeling a little bit more confident. The catch with these is lots of practice. So of course, now it's up to you. You've got questions in your textbook on page 464, question 1 to 4 to try. We'll step you through doing those, so they're a little bit easier than the questions in your work packet. Okay, there are a number of questions there. And of course, there are more questions available for more practice. Good luck. Remember to let me know if you have any questions, and I'll see you in class.